Okay, welcome back. We are going to discuss relativistic collisions now, which is going to be surprisingly simple given the depth we did with decays. We're going to discover that this process involves really the same kind of analysis. It's just we no longer have a single particle on the left side. We no longer have a decay parent. We now have an incident particle, a target particle, and we have product particles. So let's begin. The frames that we're going to be using, and just like with decays, we choose whatever frame works best for solving the question at hand. But the lab frame does have a very specific meaning to particle physicists. The lab frame refers to the frame where the target particle is at rest, and the beam particle or the incident particle is moving to strike the target particle. So the target particle being at rest means its momentum is zero. It has a scattering angle and a recoil angle in the lab frame. The center of mass frame, of course, is where the three momentums, both before the collision and after, all add up to zero. We have a single angle in order to preserve conservation of momentum in the reactants or the reaction products, the product particles. And now the incident particle, there is no target particle per se. You just have, we have particle 1 and particle 2, and they collide in the middle. And again, just like before, what happens at the moment of impact, we're not dealing with it in this lesson. We're going to have to actually touch on it a little bit later in a vague way, because we need to, like I said in a previous lesson, we need to tease out how do we isolate the dynamics. Right now, we're not too worried about it. We're just looking at what goes in and what comes out, what goes in and what comes out. Okay, so we have a standard notation that we're going to use, and this is not too divergent from what you'll see in the literature. In the lab frame, the incident particle, the one that's actually moving, not the target particle, the incident particle, its energy is E sub L. If you see an E sub L, you know you're dealing with the lab frame. And because of this, you can get rid of using that little circle all the time on top of the equal signs, because you're now actually tagging the variable itself as being specific to the lab frame. And then the momentum in the of the incident particle will be momentum lab. Remember, this guy has zero momentum, the target. So we just say 3 momentum lab frame. And that always refers to the incident particle. And then, of course, the product particles are particle 3 and particle 4. And the target particle just has its time-like component in its 4-vector. Momentum is the mass. And its space-like component is 0 because it's sitting there. You're in the frame of, this thing is sitting still in the lab. I guess it's sort of like, like the Rutherford experiment. You have some gold foil just sitting there and you're blasting it with electrons, right? So that's sort of the lab frame. The center of mass frame is exactly the way you would imagine it to be. Now the incident particle, there are 2 incident particles, but we still call particle 1 the incident particle. What's the target particle is now moving, and their total mass is, their total linear momentum is 0. So you have rho star, we put stars on the center of mass frame, and we have minus rho star for the other particle. And of course, so now you have 1 momentum for the incident particles, and you have 1 momentum for the final particles. But we label these guys with a star, not uncommon in the literature to take the center of mass frame and give it some kind of star. And again, that star will allow us to get rid of the little circle and the equal sign. And then we now have our invariants, and our invariants are different from the invariants. They have to be, there's more particles. But these are the true Mandelstam variables. I called Mandelstam variables, when we studied decay, our 3 invariants there, our 4 invariants there. And not fair, right? They are Mandelstam-like in the sense that they're invariant masses of invariant masses of subsystems, right? In this case, you have invariant masses, but they're not. The subsystems are things that are on both sides of the collision for T and U, and one side of the collision for S. So S is the invariant mass of the 1,2 subsystem that was incident. But you'll see we don't really keep an invariant mass of 3, 4. Well, S is the invariant mass of both the before and after subsystem, I guess. I guess that's the way to think about it. But T and U are called momentum transfer, and it's the invariant mass of the difference between something on the front end of the collision and something on the back end. These are the Mandelstam variables. So if you call the decay ones we use Mandelstam variables, eventually people will get it because they're so similar in nature, but the Mandelstam variables are always S, T, and U and given by these definitions in particle collisions. And just as with decays, we want to begin our research of this subject of particle collisions by coming up with expressions for EL and the magnitude of the momentum, and E1 and the magnitude of the momentum in terms of these Mandelstam variables and invariant masses, like the masses of the different particles. So we're looking for those formulas, and we're going to build those formulas up, and we're going to use very similar methods, but we're going to spend time doing that, and then we're going to kind of learn something about the relationship between the lab frame and the center of mass frame. So let's begin with that. So to start with, the process is super similar. We write down S, P1 plus P2. We blow this up. This statement is true in any frame of reference because these are all four momenta. There's nothing here to establish a reference frame. We then go into the reference frame of the lab. We can immediately write P1 and P2 as M1 and M2, regardless of being in the lab or not. These two substitutions are almost automatic when you see them. But this part, of course, is where being in the lab frame is very helpful. P1 dot P2 is immediately M1 E lab. And now we have an expression for E lab, and everything else we see is an invariant, right? Which means, kaboom, we solve for E lab right away. And now notice I've now gotten rid of the equal sign with this circle on top. And that's because we're leaning on this L. This L tells us we're dealing with the lab frame. If we just left this with an E, you'd think, oh, there's some energy there, and it must be that. You wouldn't know what energy that referred to. You would think that this is some kind of true thing in every frame. But because we have the L there, we know we're in the lab frame. So I can kind of drop it. And another thing I can solve for is I can look for the momentum in the center of mass frame. I might be interested in the momentum of the center of mass frame. That is this value, rho vector star's magnitude, right? And I can solve for that by now going into the center of mass frame, where P1 plus P2 just becomes E1 star plus E2 star because rho 1 star plus rho 2 star cancels to 0. But I just noticed I'm missing my little stars on all of these rows. Right? I need stars, and I don't have a sub 1 or sub 2 because there's only really one magnitude, right? So there's only one magnitude because of the conservation of momentum. So now I write this expression, and I immediately do the obvious substitution for E1, square root of mass 1 squared plus rho 1 squared, and E2, square root of mass 2 squared plus rho squared. And now I have that same structure that we've been used to from the decays, right? This is where our work on the decays just pays off right away. We know that this thing, when you solve for rho, this thing under the radical, when it's summed with two different numbers, you end up with this lambda function, and over 4 at 1 over 4s times this lambda function of s, m1, and m2. So now I have a solution for the initial particle momentums in the center of mass frame. And because P1 plus P2, it also equals P3 plus P4 due to momentum conservation on both sides. Remember, I guess we did that here, right? S is P1 plus P2 squared, but it's also P3 plus P4 squared. So in the center mass frame, we can use exactly the same logic we just did, where now instead of E1 and E2, we have E3 and E4, and everything follows through except for the subscripts. And we end up with the final momentum, again, missing my little star here, right? And that is the final momentum of the product particles in the center of mass frame. So you should see this kind of analysis is exactly the same. I would like to know what is the lab frame's rho? What is the rho in the lab? What is the magnitude of the 3 momentum in the lab? Now this one is a little bit of a different algebraic trip, but it should feel familiar at least. We've already solved for the energy in the lab frame in terms of the invariance. That was this expression right here. So taking that expression, well, let's just substitute right away for E lab. This substitution should be really, really straightforward and simple now. When you see the energy, the time-like part of a 4-vector, you can almost immediately substitute for this. And that's important because in QED that kind of comes up a lot. When you start studying the relativistic quantum mechanics, you start seeing a lot of those substitutions. So it should be really familiar. But once you have this, now we square both sides, and you get this guy. I brought the 2m2 over. You square everything, and you get 4m2 squared plus m1 squared L. And then squaring these pieces gives you this. And this is looking almost like a lambda. If it wasn't for that plus sign, you have all the cross terms, you have all the squares of these things squared, right? But you have a plus sign there. But interestingly, you have a 4m2 squared m1 squared, which when you bring over to the right side is going to cancel that and bring into a minus sign. So you have 4m2 squared rho. This is what we're looking for, the magnitude of the vector squared, of the 3 momentum squared. And this is actually lambda of S, M1, and M2. So now I have the magnitude of the magnitude of the lab 3 momentum squared is this lambda function again over 4m squared. So I've actually was able to solve for this as well. So now we've found a way to solve for both of these terms here, and we've also solved for this term here, rho. So now let's check them off, right? We now have an invariant expression for that, an invariant expression for that, and an invariant expression for that. So that leaves one left. But before we do that one, let's see what can we do with what we've already studied. Well, notice we've got this. We just solved for this one in the lab, the momentum, 3 momentum squared in the lab, and I don't know why. I guess I should have to be consistent. And we've also solved for the 3 momentum squared in the center of mass. And notice these two delta functions are the same. It's SM1M2, SM1M2. So I can actually find a ratio between the lab 3 momentum magnitude and the center mass 3 momentum magnitude. And when you divide this by this, you basically end up with this expression. That there's the relationship between the center of mass momentum and the lab momentum is just m over the square root of s. And that is a very interesting relationship. We'll study it a little more later, but we're going to put it on the shelf for now. But it would be nice for us to also have a relationship between the center of mass energy of the incident particle with the lab energy of the incident particle. This will actually tell us a little bit about how to build an accelerator. So we kind of want to know this. But we've figured out E lab, but we haven't figured out an expression with using invariance for the center of mass energy. So now we got to do that. And that one is actually a bit more tricky than the others. Okay, so let's see. Is it possible for us to find something that looks a little like this, but we're dealing with now a solution for E1 star, the incident particle center mass energy? So we begin with this definition, right? The square root of the invariant S is going to be E1 squared plus E2 squared in the center of mass frame. That's just taking P1 and P2 and adding them together in the center of mass frame. The 2 momentum components cancel, or the 3 momentum components cancel, and all you're left with is the time-like component. The 3 space-like components cancel is the proper way to say it, and only the time-like component adds together, and that's what this is. And of course, there's no 0 here because we've got these asterisks here. So that is just sort of the definition of S. This is the conservation of momentum, right? We're in the center of mass frame. I'm sorry. This is the definition of the center of mass frame, right? This is the magnitude, right? This part here is the magnitude of rho let's see, right? These are the magnitudes of the first particles, magnitude through momentum, and the magnitude of the second particles. But because you're in the center of mass frame, these two numbers as magnitudes should be equal. The momentums themselves as vectors, right? They would be opposite, but as magnitude squares, they're going to be equal. Now, since ultimately we're looking for a formula for just E1, this is going to take some manipulation, but we want to do this as our next step. E2 squared equals M1 squared minus M2 squared. And you might motivate this by saying, well, I want to keep the invariant stuff. I want the invariant stuff on the right, and I'm looking for a formula for E1, so maybe this is a way of getting there. And our next step will be to factor the left-hand side. So I get E1 star, oops, not squared, but E1 star plus E2 star, and then E1 star minus E2 star equals M1 squared minus M2 squared. And with this, we can immediately make a substitution. Oops, look, I think I did something wrong here. There shouldn't be squares here, right? Right? S itself, S equals E1 star plus E2 star squared, right? So the square root of S gets rid of that square. So I don't need squares there. And the reason I noticed that, of course, is because I'm about to take that and substitute it right here. Or I guess the way I should write that is I'm about to take the square root of S and substitute it right there. And if I had those squares there, I couldn't do that, right? So I knew that was wrong. So this becomes, and that's the expression after this substitution. But so now I'm doing really well. I've got one E2 left that I've got to get rid of. And I can actually lean on this expression again, right? I just solve this for E2, and I get square root of S minus E1, square root of S minus E1, and that I substitute right there. So let's do that. And after that substitution, I'm left with this expression where now everything is E1 and a bunch of S's. So I just want to isolate E1, and my problem should be solved. So we just expand this, and we end up with 2 square root of SE1 minus S, and this immediately solves to something that does, in fact, look just like what we wanted, right? S, whoops, not minus, but S plus M1 squared minus M2 squared divided by the 2 times the square root of S. So in this case, the formula does, in fact, look very similar to the lab formula. Right, where did I put the lab formula? Right, so here's the lab formula up here, and here it is down here. In fact, it comes down to the denominator and a sign. I mean, you couldn't intuit this at all, but it was much harder to derive this formula. We had to know a few facts. We had to implement the definition of the frame. We couldn't just use one of these invariants and kind of paw our way through it. So that's a sort of evidence to me that there's a lot of asymmetry in the algebra here, right? And the reference frames as well. Okay, so now, but our goal is to find a function like this. So now we need to put these two guys next to each other and see if we can tease that apart, tease this function out of it. And I've actually worked it out right here. Here are the two expressions. And what our strategy is going to be to take the right-hand side of the center of mass expression and turn it into the lab expression as best we can, and then make a substitution. So I need to turn this plus M1 into a minus M1. So I'm going to add a minus 2M1, and then, well, I'm going to subtract 2M1 squared. These are squares, not linear. And then I'm going to add it back. So this is 0. So then when I've done that, I have S minus M1 squared minus M2 squared, which is this, right? This expression right here now appears right there in the numerator, but I've got this additional 2M1 squared, right? So I'm getting there. So I'm going to make a substitution for EL. I'm going to take this 2m2, move it over here, so I have just that expression isolated, and I'm going to substitute 2m2 2m2, right in for this part, right? So that's what this is, 2m2 elab, substituted in, just like I said, and you get the 2m1 squared left over 2 square root s. And when you take this all apart, you divide out, you clear out the 2's, you get the center of mass energy of the incident particle is a function of the lab energy of the incident particle. And everything that is part of that function is an invariant. So this tells us something very important, right? This expression here, we can actually use that to help us understand how colliders work. And so let's run through a good example of that before we quit for the day. Actually, there's not quite enough time to go through the collider example, so let's just finish up with a few extra notes about the Mandelstam variables. Right, with this being our general collision process, and with time moving from left to right, time is moving in this direction, and so these two particles, P1 and P2, are colliding, and the output particles are P3 and P4. And with that in mind, we can define a few different processes that use these Mandelstam variables to identify the nature of the process. Unfortunately, we have to kind of break our silence about what is happening inside this process, right? We're going to now talk about that collision zone and the dynamics, but we're not going to go into it much, but we are going to say, okay, let's take a look at this example where P1 and P2 come together at this vertex, and they form a photon, and then the photon decays into the final products. So that's talking about the dynamics of this process. But what's important for us is being just pure, relativistic kineticists, right? All we're interested is in the kinematics, relativistic kinematicists, I suppose. We know that momentum is conserved at this point, and actually when you do QED calculations, you deal with each vertex very carefully. But imagine that everything is on shell at this point, meaning momentum is completely conserved right here at this point. And if that were the case, then Q would be the sum of P1 and P2, right? Q would have to carry off the momentum of P1 plus P2, which is exactly kind of what S does, right? S is P1 plus P2 squared, which in the center of mass frame would be E1 plus E2 squared. And so we call this process the S-channel process. This concept where the two particles come together, form a photon, and the photon goes off to the right, that is an S-channel process because Q, the momentum of that photon, is best connected to the Mandelstam variable S. Now, you can look at the same process like this, right? P1 and P2 are still colliding because time is still moving from left to right. But now that photon doesn't really connect P1 and P2. It's, this electron is in the story of the Feynman diagram, emits this photon and becomes this positron. And this positron comes down and absorbs that photon and becomes this electron, or the other way around, or both at once, right? But now Q, the momentum for Q is P1 minus P3. That's what's left over for Q. And P1 minus P3, of course, is the T-channel process. So, so Q squared is actually equal to T. So that is called the T-channel process. Now, also, if you look at this and you calculate Q squared in such a circumstance, now, if the process were elastic, which means that the energy of particle 3 would equal the energy of particle 1, then you find out that Q squared is actually less than 0. So in this case, this photon has actually got a space-like 4 vector. We're over here, this calculation, E1 plus E2 is always greater than 0. So that is a time-like 4 vector, which is kind of interesting. But then, of course, you have the U-channel process, where now the first particle comes in, emits this photon, but it's not P3 that comes out, it's P4 that comes out. And the U-channel process, which is this sort of crossing process, that is P4 minus P1, right? So that's called U channel. Okay, so we've kind of looked at, so that's just an idea of when you get to QED, or quantum electrodynamics, you'll see S channel, T channel, and U channel processes, and they're related to these Mandelstam variables. And sometimes these are called momentum transfer, right? Because P1 minus P3, that's the momentum of this photon, and that photon is what's transferring momentum throughout this tree diagram. So T is called the momentum transfer, and U is likewise a momentum transfer. So T and U are often called momentum transfer, and that's based on the idea that this photon is what's carrying the momentum inside this Feynman diagram. So all of the mystery of what's happening in here, there's momentum being transferred, and there's charges being transferred and charges being created, as long as the net charge created is zero, and charmness and strangeness and all of these other cool things that are happening. One of those things is momentum transfer. And that's what these Mandelstam variables help us understand. Okay, so let's close out. Today we had a look, we developed some formulas for collisions. We developed lab frame formulas. We developed some formulas for the center of mass frame, center of mass momentum, lab momentum, very similar formulas. Differences here in the denominator a little bit, right? Difference here in the sign of these masses in the denominator. Everything looks kind of the same. This one was easy to derive. This one was a little harder to derive, if you remember right. And ultimately, we got this formula, which we'll use a bit in our next lecture when we talk about the implications of energy in the lab and energy in the center of mass. That's a very famous fact, right? It's a very famous fact that it's hard to do things in the lab frame. If you set up an experiment in the lab frame, you're wasting a lot of energy in linear momentum. If you set it up in the center of mass frame, your experiment has much greater access to interesting phase space, or more energy is available for the creation of new particles and resonances. So that's a famous fact that we really, really have to cover. And then, of course, we talked about the Mandelstam variables, which are given here. And eventually, there are many, many constants, just like E1 and EL and these rho. These depend just on S. You only see S introduced here. But there's others, especially angular variables about recoil angles and scattering angles, where you start getting T and U as part of the formulas. You want everything to be expressible in terms of Lorentz invariant scalars. And these are the Lorentz invariant scalars you want to use. These, and of course, the masses. The masses are called trivial scalars. These are a little bit more interesting scalars. And then we talked a little bit about the ultra-relativistic limit of these things, where these masses can be discarded. Now, in the next lesson, I'll show you examples to give you real good confidence that, yes, you can just throw away these masses. You'll see how many decimal points we actually just are beyond our calculation by throwing away these masses. But when you throw away these masses, you are saying that these particles are moving at the speed of light. But of course, when you are in a position of ultra-relativistic limit, the particles are in fact moving at very, very, very close to the speed of light. So it all hangs together. And then I pointed out that the sum of the Mandelstam variables is the sum of the total masses of all the particles involved. And in the ultra-relativistic limit, that goes to zero. Okay, so the next lesson will be a lot more practical application. We'll actually run some numbers through these formulas and do a problem that I pulled off of the internet somewhere. And I'll see you next time.